This is the first video in a series of 5 videos about abstraction logic. So abstraction logic is logic I've been working on since basically 2021. And recently I've started writing up everything I know about abstraction logic in a book. So the book is still a draft, it's incomplete. There's still lots to do in abstraction logic, and so both my knowledge about abstraction logic and the book will evolve still over time. So in this first video, I will talk about my motivation to work on abstraction logic. The second video will then introduce the mathematical universe. The third will be about abstraction algebra, and then the fourth will be about abstraction logic proper. And I also have a concluding video. So in the medium 3 videos, mathematical universe, abstraction algebra, and abstraction logic basically correspond to the current chapters of the abstraction logic book, which you can download for free at abstractionlogic.com. So the computer is my favorite tool. I'm using it to create all sorts of things, mostly programs. And for useful things, there's always a question, does it work as it should? And that's not an easy question to answer for the final product, and often it's even a difficult question to pose in the first place, because what exactly does it mean? How exactly should it work? And but the thing is, we usually construct something in a modular fashion, and often when we break down a problem into its components, then the components, for these we can pose this question and answer it in a more precise and mathematical way. Okay, and that's often the reason why we break things down into components in the first place. And so a deep passion of mine over the last 30 years or so has been to unify programming, designing, reasoning, understanding, and math, because I've always sensed that, you know, they share this property of you can do it easier. It's easier to do these things if you can break something down into components and tackle the components separately. And well, if you want to put them afterwards together again, then of course you should know something about how these components behave again. So I've worked on various projects. After my diploma in mathematics, I joined the Isabel development team for my PhD, and there I worked on a formal proof of the Kepler conjecture, and that project was called the Fleißberg project. And so here, and as part of the Isabel development team, I learned a lot about theorem proving, how it's done these days, interactive theorem proving on a computer. And so I learned a lot there about how it's done in the small. And obviously, I also recognize that there is a need for doing theorem proving in the large. And that inspired the ProofPeer project. And I joined the University of Edinburgh for this project. And I worked on it together with Jacques Fleuriot, David Aspinall, and Phil Scott. And so there the topic was collaborative theorem proving as an evolution of interactive theorem proving. And yeah, so I had a lot of time during this project just to think about theorem proving, about how I would like to do theorem proving, and, you know, a little bit more deeper questions about theorem proving in general. So afterwards, I worked as a freelancer on various projects. For example, game development, and I also worked for a few years on developing a custom computer aided design application that runs on the iPad. And as part of that, I developed some algorithms, and again, the question was, how do I make sure that these algorithms that were actually quite complicated, because they were also tuned for performance to run on Apple Metal's shader architecture. And so the question is, is this really correct, what I'm doing here, for example? And again, so we usually construct things in a modular fashion. If we can break them down into components, it becomes easier to answer the question, do these components work as they should? We can often even make it turn it into precise and mathematical questions and answers. And so what I've learned is I really want a tool that helps me with posing and answering such questions in a precise and mathematical way. So I want a tool for practical logic. And this is how the idea of Practa was born. Practa is short for practical logic, and it's about enabling your vision by precision. Practal has a bigger scope, of course, but at its heart, it's really a system for interactive theorem proving, similar to Isabelle. So, well, when I say it is a system, Practal doesn't exist yet. I'm working on it, I'm conceptualizing it, and abstraction logic is part of Practal's design, but the software itself doesn't exist yet, and I'm working on it. So, and I'm designing it from the start. From the start, I have in mind that, look, there is strong AI now out there, and we have to take this into account. We have to be able to provide natural language support based on LLMs, and as we have seen with something like AlphaProof, we also know that we can take advantage of strong automation in the very near future, and we have to take this into account when designing such a system now. And but automation is actually already pretty good for existing theorem provers like Isabelle. So now that I'm working on a new logic for Practa, abstraction logic, so why am I working on this logic still using paper and LaTeX, and why am I not using Isabelle? I mean, I'm an expert in Isabelle. And I think I have the answer to this question. It's the logic, stupid. I think I'm just not very comfortable with the restrictions that existing logics place upon me, which have been implemented in existing proof assistants like Isabelle. And so the choice of the logic that you choose for a system such as Practa, you cannot change it later on. It will determine which logic you choose. This choice will be with you forever and your system. And current systems, they have mostly these three kinds of logics, either first order logic, second order logic, or a type theory based logic. And first order logic is probably the most popular logic among mathematicians, if they care about logic at all. But its problem is that it has no it has no constructs for general binders. The only constructs it has, the only for general binding, are universal quantification and existential quantification. Second order logic is not much better in that respect. According to Quine, it's really just a set theory in sheep's clothing, and it still has no general constructs for new binders. Now, type theories, they do have the facility for general binders. And I'm going to argue that they really all trade for this facility a limited view of the mathematical universe. Apart from that, I think another negative aspect of type theories is that often they don't have difficult or non-clear or non-existing semantics because they are based on proof theory, and proof theory often, people who like proof theory often think that mathematics is just a game of syntax and rules, and that there is not much meaning to it. For Practa, none of the above logics really cuts it for me. I want the facility of general binders, but I also want the unlimited freedom that I find in first order logic. And interestingly, although for a system such as Practa you have to answer the question which logic up front, this is not a question you have at all when you do mathematics, right? So mathematicians usually don't care about the logic that they're working on if they're not logicians. I think abstraction logic reflects that, because abstraction logic, it's not one of many logics. I think that abstraction logic is the one logic, okay? It's the one foundation, and that's also why I think it's, of course, the right logic for Practa. It's a logic you can install once, and then you can forget about the logic. You don't have to think anymore, or do I need a special logic for this or for that, because you have this common foundation, and you just accept it. And interestingly, I still believe in foundational pluralism. So this is not a contradiction here. We will see later that abstraction logic, yes, it is the one logic, but it also works as a logical framework, because it presupposes basically nothing about your mathematical theory. So you can really do any mathematics you like in this logic.